horizontal asymptotes happen when you take limits at infinity and you end up with a number. So we say that a function f has a horizontal asymptote at the line y equal b if we can show that the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. So let's find the horizontal asymptote for the function f of x is equal to 1 over x. We have the graph over there, and we can look at the graph in a second, but let's find the asymptote here. How do we do that? We take the limit as x approaches infinity or negative infinity, it doesn't matter which one, of 1 over x. Well, this we know we use the theorem above. Anytime you have a rational function and it's a number over x to a power, this is equal to 0. Since this is equal to a number, therefore, these three little dots like this in a triangle means the word therefore. So therefore, we have a horizontal asymptote at y equals 0. And if you look here, if I were to draw in the horizontal asymptote, you notice that, yeah, that makes sense, because as we go towards positive infinity or negative infinity on the x-axis, my graph is trying to get closer and closer and closer to the line y equals 0. So to find horizontal asymptotes, what do? We take the limit as the function approaches infinity or negative infinity. So please note that polynomial functions of degree 1 or higher, so any polynomial, does not have asymptotes. So when you're asked to find asymptotes, vertical and horizontal, if you have a polynomial, it won't have any vertical or horizontal asymptotes. So the next part of this section, the next three examples, all we're looking for is finding horizontal and vertical asymptotes if any of the following functions. So let's start with number 11. The first thing I'm going to do is vertical asymptotes. So that's like the beginning of this section. So recall, with vertical asymptotes, what do? We try to factor and reduce. Well, I can't factor my numerator and I can't factor my denominator. So what I need to do then is set the denominator, in this case, t squared plus 9 equal to 0, and solve for x, or t in this case. So subtract 9 from both sides. I get t squared is equal to negative 9. Take the square root of both sides to solve for t, and I end up with t is equal to plus or minus the square root of negative 9 is 3i. This is an imaginary number. So step 3 for vertical asymptotes said that we're going to have a vertical asymptote anywhere we ended up with a real number. Did we end up with real numbers? No, we ended up with things that were imaginary. So for this particular graph, we have no vertical asymptote. What about horizontal asymptotes? Well, to find horizontal asymptotes, we're going to take the limit as t goes to positive infinity or negative infinity, either one, of our function t squared over t squared plus 9. Well, this is a rational function. How did we deal with that? Well, we said what we needed to do is we needed to look at the highest term in the numerator and the highest term in the denominator. So this is equivalent to looking at the limit as t approaches infinity of t squared over t squared. Well, that reduces to just 1. So we're looking at the limit as t goes to infinity of 1. Well, what's the limit of a constant? The limit of the constant is the constant. Therefore, we're going to have a horizontal asymptote at the line y equal 1. Where did 1 come from? That's the limit as we went to infinity. Number 12, we have f of x is equal to 2x squared plus 11x plus 12 over 2x squared plus 5x minus 12. Again, let's start with trying to find those vertical asymptotes. So step 1 was to factor and reduce. So let's see here, the numerator. Let's see if it factors. So the only thing that multiplies to a 2x squared is going to be a 2x and an x. Same thing for the denominator. For the numerator, I need things that multiply to 12. And then when all multiplied together are going to add to an 11. So let's try plus 4 and plus 3. Let's see if that works. So we have 2x squared plus 8x plus 3x is 11. Perfect. For the denominator, again, it needs to get to 5. Well, if I do a plus 4 here and a minus 3, that'll get to 5. Let's check. 2x squared plus 8x minus 3x is a positive 5x minus 12. Perfect. Can we reduce? We sure can. They have that in common. So then the second step for vertical asymptotes is to set that denominator. The only denominator I have left is 2x minus 3 equal to 0 and solve for x. So 2x minus 3 is equal to 0. Add 3 to both sides, divide by 2, and x is equal to 3 halves. 3 halves is a real number. Therefore, we have a vertical asymptote at x equals 3 halves. What about horizontal asymptotes? Again, for horizontal asymptotes, we're going to take the limit as x goes to infinity of this function. So we have 2x squared plus 11x plus 12 over 2x squared plus 5x minus 12. Well, the leading term in my numerator is 2x squared. The leading term in my denominator is 2x squared. So this is the same as just looking at the limit as x goes to infinity of a 2x squared over 2x squared. Well, 2x squared over 2x squared will reduce to 1. So we're looking at the limit as x approaches infinity of 1. Well, 1's a constant, right? And the limit of a constant is the constant. Therefore, we have a horizontal asymptote at the line y equal 1. That's it for section 2.2, where we looked at limits at infinity and infinite limits.